Hi, in this video, I will be talking about the Bose-Einstein condensation. A brief introduction before going to the main topic. The Bose-Einstein condensate is a state of matter in which separate atoms or subatomic particles cooled to near absolute zero coalesce into a single quantum mechanical entity which can be described by a wave function on a macroscopical scale. The particles that follow the Bose-Einstein statistics are called bosons. A BC is formed by cooling a gas of extremely low density, about 100,000th the density of normal air, to ultra low temperatures. So in this diagram, we can see an illustration of the Bose-Einstein condensate. This is the velocity distribution data in three different views at maybe three different time steps. For a gas of rubidium atoms, which confirms the discovery of a new phase of matter, the Bose-Einstein condensate. The left image shows the velocity distribution just before the appearance of a Bose-Einstein condensate. The center image shows the velocity distribution just after the appearance of a Bose-Einstein condensate, and the right image shows the velocity distribution after further evaporation, leaving a sample of nearly pure condensate. Now, a brief history. How was the Bose-Einstein condensate discovered? In 1924-25, Satyendranath Bose sent a paper to Einstein on the quantum statistics of photons, in which he derived Planck's quantum radiation law without any reference to classical physics. Einstein extended Bose's idea to matter, and the results of their efforts was the concept of a Bose gas. This gas was governed by the Bose-Einstein statistics, which describes the statistical distribution of identical particles called bosons with integer spin. Einstein proposed that cooling bosonic atoms to a very low temperature would cause them to fall or condense into the lowest accessible quantum state, resulting in a new form of matter called Bose-Einstein condensate. It is observed in not only isolated atoms like rubidium, sodium, and lithium, but also in hydrogen and helium. Next, we come to the critical temperature. So, in the previous slide, we had seen that the bosonic atoms were cooled to a very low temperature. What is this threshold for the temperature? This is the critical temperature. The transition to Bose-Einstein condensate occurs below a critical temperature, which for a uniform three-dimensional gas consisting of non-interacting particles with no apparent internal degrees of freedom is given by this equation as it is, where we see Tc is the critical temperature, N is the particle density, or you can say the number of moles, M is the mass per boson, Kb is the Boltzmann constant, and this is the Riemann zeta function, approximately equal to 2.6124. Next, we come to the formation of the Bose-Einstein condensate. So, we have already learnt about the Bose-Einstein and the Fermi-Dirac statistics. Bosons are the particles that follow the Bose-Einstein statistics and have integer values of angular momentum quantum numbers and symmetric wave functions. Fermions, on the other hand, are the particles that follow Fermi-Dirac statistics and have half-integer values of angular momentum quantum numbers and antisymmetric wave functions. In class 12, we have studied the Pauli's exclusion principle, which states that no two fermions can occupy the same state at the same time. For bosons, however, the Pauli's exclusion principle does not hold. Hence, all the bosons can be in the same state at the same time, and when this happens, they all condense to form a single form of matter called the Bose-Einstein condensate. This is best explained by using an illustration. In this figure, we can see that the atomic clouds of the lithium, a boson with 4 neutrons, continue to collapse as the temperature is lowered. Since identical fermions cannot occupy the same space, as we just saw with the Pauli's exclusion principle, the atomic cloud of Li6, a fermion with 3 neutrons, shows a smaller collapse. So, due to the bosons occupying the same state, there is a larger collapse, while due to the selective occupancy of the states by the fermions, there is a smaller collapse in case of fermions. Now let's look at some properties and potential applications of the Bose-Einstein condensate. So, one of the most commonly known properties of the Bose-Einstein condensate is their superfluidity. Since they are effectively superatoms, Bose-Einstein condensates are all moving in the same way at the same time when they flow and don't have energy losses due to friction. Obviously, there is no collision whatsoever. Due to this, they pose as the best lubricants, though are very expensive. Yeah. Meanwhile, the characteristics of BCs, the Bose-Einstein condensates, and their response to sound and other disturbances are still under investigations. So this is a potential application. Once these experiments are proved successful, they could be used in a wide variety of applications whatsoever. Next, we come to another interesting properties of Bose-Einstein condensates, which is that they can be fashioned into a beam and they behave like laser in their coherence. This way, an experimenter can know how a part of the beam will behave at every single location. And this property of lasers has been used in the past for etching purposes. A, a Bose-Einstein condensate beam would have greater precision and energy than a laser, because even at their low kinetic energy state, the massive particles would be more energetic than the massless photons. The major technological concern with Bose-Einstein condensate beam would be getting a clean enough environment for it to function repeatedly and reducing the cost of Bose-Einstein creation enough to use Bose-Einstein condensates regularly in beams. This, like we saw before, is also currently under observation, and with further experiments, we hope to get a groundbreaking application in the future. However, Bose-Einstein condensate beams or atom lasers could produce precisely trimmed objects down to a very small scale, possibly a nanotech scale, which is a huge implication of Bose-Einstein condensates. So with this, I come to the end of the Bose-Einstein condensation for today's lecture.